Hi friend, you are welcome back to my channel, and in today's video lesson we shall be talking about another important topic in physics, which is frictional force. So without wasting your time guys, we'll be getting started now. Now there are some key symbols I'll be making use of that I want you guys to take note of their meaning and if possible their formula before we get started. Now you have F arrow. F arrow stands for frictional force. And the formula, the most common formula for frictional force you know is mu times n, where mu, as we have here, is what? The coefficient of friction. Now n is normal reaction. Do I add it here? It's normal reaction, or you say the normal force. Then you have F subscript n. This is the net force. And the net force can also be gotten with a formula which is mass times acceleration. Next you have P. P under frictional force stands for the applied force. Okay? And then you have mu. Mu stands for the coefficient of friction. And under inclined plane scenario, like we have there, mu is equals to tan theta, where this theta is the angle of repose, or you say the angle of friction. I hope that is clear. And then we also have W, and W as we all know is what? Weight, the weight of the body. So guys, now we know this, let's get down to something more different. We shall be looking at the motion of single masses, a single mass. Here you have a single mass, and here you also have a single mass. We shall be looking at how friction applies to them and how we can solve questions under them. Now, this is a first scenario. This is sub A and this is subset B. Subset A and subset B. Under case 1, we have two subsets, A and B. Now, this is the first scenario we described here. This is a body of mass M with gravity acting downward on it. Therefore, it possesses a weight W with a reactional force acting upward called the normal reaction, symbolized by N. Now, an applied force is applied in this direction because say P stands for what? Applied force. Now, this applied force experiences an opposing force in the opposite direction, which is F arrow, which stands for what? Frictional force. So this is scenario we describe here. Now, when these very bodies start moving in the direction of the applied force, there are formulas you can use to work any questions when asked under this. You have the first formula, which is the general formula. Applied force is equals to net force plus frictional force. Just a statement of general facts. Now, we can further expand this to be applied force is equals to, in place of net force, we can say the mass times the acceleration that we have here. Plus, in place of frictional force, we can say mu times n, where mu is what? The coefficient of friction, and n is the normal reaction, or you say the normal force. Then we can further expand this again, guys. You have applied force is equals to ma plus mu w, because under this very scenario, it is assumed that the normal reaction and the weight of the body are equal. So in place of n, I can sometimes use w. So if I was given the normal reaction directly, I will use this formula. But if I was given the weight of the body directly, I will use this formula. That is for this. And then this is another scenario under case 1. This is another scenario. But in this very case, observe something. There is a difference. The applied force in this case is acting at an angle to the horizontal. But in this case, the applied force is acting at the horizontal direction, along the horizontal direction. So now in this case, this is what we have. Applied force acting at an angle theta to the horizontal direction. So we won't use the same formula because it's going to be a different thing entirely. The rest scenario, net force acting in this direction, normal force acting in this direction, the weight acting in this direction, the frictional force acting in the opposite direction, they will remain the same like as in A. So how will the formulas now look like when this body starts moving? We can say P cos theta because we have to resolve the applied force and get the horizontal component that will actually move this body in this direction. And the horizontal component of P when it's acting at an angle theta is equals to P cos theta. The rest variables will remain the same. Okay? Ma plus the frictional force. Now we have this. We can then continue and say P cos theta will now be equals to Ma added to mu n. Like I said, frictional force is mu n, while net force is Ma. Okay? Let me just quickly put that here in the first place. This is going to be Fn plus frictional force. So now we have this now. We can further expand and say P cos theta is equals to Ma plus mu. Now this n can be replaced by something, but in this case not W. Okay? Because the applied force is not acting along the horizontal axis. Now observe something. What are the forces that are acting upward there? You have N that is the normal reaction, and there is a component of the applied force that is also acting in the upward direction. I repeat, N is acting upward, and a component of the applied force is also acting upward. That is P sine theta. So you have N plus P sine theta. These two upward force is balanced by this only one downward force, which is W. So N plus P sine theta is equals to W. Now because we are trying to look for an expression for N, if you make N subject in that expression I just said, N will be equals to W minus P sine theta. So another formula we can get from this point is P cos theta is equals to Ma plus mu in brackets W minus P sine theta. So these are the formulas that apply when the body is moving with an applied force applied at an angle theta to the horizontal along the horizontal plane, because the plane in this place is horizontal, is it not? It's moving along an horizontal plane. So guys, take note of this important formula. So we go straight to this one. Now in this place, the body is being made to move on an inclined plane, and the inclined plane have an angle theta. Okay, so the inclined plane of angle theta is upon which the body rests. So if this body starts moving, what are the formulas that will apply? P, which is the applied force in this direction, will be equals to Fa. Let's just call this first. In the first place, let's call it Fn. F subscript n. Okay, better still. Now we have this Fn plus F arrow. Now if this is the general formula, how can we expand this further? Now if you resolve the weight, now the weight of a body is due to gravity. Gravity acts vertically downward, and that's why the weight is in this direction. You don't have to, should I say, change things just to make it suit you. You want to put the weight along this line of action so that we balance the normal reaction. That is wrong. Gravity, as we know, acts in this direction. So the weight also acts in this direction. I hope that is clear. But the normal reaction acts upward along the plane of the inclined plane. It's acting upward along the inclined plane. That is, it's acting perpendicularly to the inclined plane. But the weight is acting vertically downward on the inclined plane. So this is what we now have. So from here, guys, observe something. If we resolve the weight, we draw this down, we cover it like this. This component of the weight is equals to P. And what is that component? If here is theta, this component is called W sine theta. I just want to make this easy, that's why I did not complex the diagram, okay? But P is equivalent to W sine theta. And then, like we all know, in place of net force, you can say Ma, and then we can continue in place of frictional force, you can say mu times the normal reaction. So this is another formula you can use depending on the variable. So if I was giving normal reaction, this is the formula I should use because this is the one that contains normal reaction. Is it not? Good. Now there are further ways you can actually expand this very formula. W sin theta will now be equal to Ma plus mu times, there's an expression for normal reaction we can get from this diagram. Now observe something. The the weight is acting vertically downward, and if you draw this down to balance this at an angle theta, which is equal to this theta, the component of weight that is acting in this direction is W cos theta. So in place of n, I can say W cos theta. N is equal to W cos theta. So this is a further expanded version depending on the variables, okay? That will not depend on the formula you will now pick, okay? So this is for motion of a single body or a single mass. Now what if more than one masses or bodies were connected together and they were made to move under the influence of frictional force? How will the motion look like? How are we going to describe the motion? So that will bring us, guys, to motion of connected masses. And that's how we got here. Now there are different cases depending on how the structure on which they are moving depend. Okay, this is case 1. This is a pulley, like I've already described before, under simple machine. This is one pulley, and two bodies are connected together. One is bigger than the other. So this pulley will move in the direction of the bigger mass. Is it not? Good. And as it's moving, it will experience an acceleration. Because when a body is in motion, acceleration is, should I say, possible. Okay? It's possible that the body has an acceleration. Okay? Now observe something. This mass, the weight acting on this mass is acting downward. But there is an upward force that is counterbalancing it in this very rope. That force is called the tension. On this other side, the weight of M2 is acting downward, but there is an opposing force that is acting upward to balance it. That is called the tension too. And I must bring to your notice that the tension in this side, M1, is equal to the tension in this other side, in M2. So I just say TT. I did not say T1 or T2 because it's the same tension. Okay? Now this is what we now have. If you were not asked, because under connected masses, the two things you are most likely to be asked is to find the acceleration or the tension in the rope. To find the acceleration or the tension in the rope. Now that's why I just give you the two formulas. Now for this very case, where two bodies are connected over a pulley, to get the acceleration, because this is the bigger mass, M2, it will be M2 minus M1 over M1 plus M2, the final of what you get here, times gravity. That will give you the acceleration. And mind you, the acceleration of mass A or mass M2 is equals to what? That of M1. So they are moving with the same acceleration. Likewise, they have the same tension acting on them. To now get the tension acting on any of these two bodies, the formula to make use of is 2m1 m2 divided by m1 plus m2, the resultant of what you will get here, times gravity. That will give you the tension in these ropes, and both of the tensions are the same. So guys, this is for case 1. Now we have known this thus far. We'll be looking at other cases. So let's have those other cases now. Alright, under connected masses, motion of connected masses, we still have 2 more to go. We have case 2. Now observe case 2. One body is acting along an horizontal plane, while the other body is hanging vertically. Now if this was what was given, okay? Remember, the idea is that mass 2 is bigger than mass 1. So the body tends to move like this. The two bodies tend to move in this way. Now at this very point on the pivot, the acceleration is A. Now in each of the rope, you have T, tension T, acting the opposite direction to their weight. And the tension here and the tension here are the same. So we use T and T. If you were now asked to find the acceleration of these two moving systems, these two masses, what's the formula to use? It's A equals m2 over m1 plus m2, whatever you get as a resultant of this, times it with gravity. It's not m1, it is the weight of the hanging mass that we use here, m2, the bigger and the hanging mass. Now to get the tension in each of these ropes, which is the same tension, T is equals to m1 times m2, like you have here, over m1 plus m2. The resultant of what you will get here times it with what? Gravity. That will give you the tension in each of these ropes. Now this is for case 2. One body is on an horizontal plane, while the other body is hanging vertically. Now for case 3, lastly, One body is on an inclined plane, the other body is hanging vertically. So what is the formula to get your acceleration and your tension? For acceleration, this is the formula to use. m2 minus m1 sine theta, because it is m1 that is on the inclined plane. So the angle theta will have to affect m1. I repeat, m2 minus m1 sine theta, likewise over m1 plus m2 as usual. The resultant of what you will now get here times with what? Gravity. That will give you the acceleration. So now get the tension in each of these groups, which are the same tension. Use this formula. m1 times m2 in bracket 1 plus sine theta. So what you will get from 1 plus sine theta? The theta here is the angle of the inclined plane. Sine of the angle of the inclined plane added to 1. What you get, use it to times m1 and m2. Everything you will get divided by m1 plus m2. Whatever you now get as the resultant of this whole thing times it with gravity, you will get the tension in either of this row, which is the same tension. Now I must bring to your notice that sometimes the value for the coefficient of friction will be given, because under this motion of connected masses, all the formulas I've given you for A and T are only if and only if the surface on which they are moving is frictionless. There is no friction. But if friction was given, there is a different way you follow it up, okay? Usually, you will minus the frictional force from the up guy. This is m2g. I will say m2g minus FRO over m1 plus m2. That's how it works. You just minus the frictional force from the numerator. I repeat, minus the frictional force from the numerator and divide by what you have as the denominator. Minus the frictional force from the numerator. So after I have times all this with g to form one single numerator, I will minus the frictional force before I divide with m1 plus m2. Like I said, this is just an explanation series. When I start doing my calculation series, I'll make sure I treat all this in details and you understand better by then. Thanks for watching this video on frictional force. I trust you find it helpful. See you guys in my next video.